Lecture 2.2, Introduction to Celestial Mechanics and Polar Coordinate Systems. We'll first review vector notation. So we'll write vectors as letters with little arrows above them, or occasionally just as a bolded letter, although in our lecture notes they'll almost always have a line, an arrow above it. If the symbol for our vector doesn't have the arrow above it, it means that's the magnitude of the vector, so which you can calculate from its Cartesian coordinates using the Pythagorean theorem. Unit vectors have hats. So a unit vector with this wearing this little hat is the vector divided by its magnitude. So this is a vector that has unit length that points in the direction of the original vector. Remember that dot products are written as a dot b. In terms of Cartesian coordinates, it's ax bx plus ay by plus az bz. You can also write it as the magnitudes of the vectors times the cosine of the angle between the vectors. And the cross product, the magnitude of the cross product is given by their magnitudes times the sine of the angle between them. We'll write Cartesian unit vectors as either I hat, j hat, k hat, or equivalently x hat, y hat, z hat. So I hat is the exact same thing as x hat, j hat is the same as y hat, k hat is the same as z hat. So we'll go back and forth between those two notations. All right, let's now talk about the dynamics of planetary orbits using Newton's laws. We're going to assume that the sun is a lot more massive than the planets orbiting it, so we'll assume that the sun is fixed in space. So there's the sun, we'll give it a mass capital M. There's our planet, say the Earth, it'll have mass little m. R is a vector that points from the sun to the planet. The dotted line will be the trajectory or the path of the orbit as the Earth orbits the sun. And its velocity through space will be tangent to that trajectory and is given by the vector v. So the equation of motion is just F equals ma. The gravitational force between the planet and the sun was again discovered by Newton and deduced from Kepler's observations. Newton found that the gravitational force is proportional to the product of the masses divided by the distance squared. G is the constant of universal gravity, and r hat is a unit vector that points in the same direction as r. So it points from the central object, the star, the sun, say, towards the planet. So the negative sign means that the gravitational force is in the opposite direction as that unit vector, which means it's an attractive force pulling the planet towards the sun. Before we look at more complicated scenarios, let's first think about circular orbits. So imagine that the planet is orbiting the sun in a circular orbit with radius r, and we'll say that the velocity is v CIR for circular. To find that circular velocity, we can set the centripetal force equal to the gravitational force. So the centripetal force is mv squared over r. The gravitational force, the magnitude of it, is gmm over r squared. The m's cancel, one of the r's cancel, and we find that the circular velocity is the square root of gm over r. So a very simple result from introductory physics. The period of the orbit, that is how long it takes the planet to orbit, can be found by taking the circumference, the distance that the planet has to go to make one orbit, and divide it by what that velocity is. So the distance over the velocity is the time. Plug in the expression for the circular velocity, simplify. If we square both sides, we actually get that the period squared is a constant times the radius cubed. This should look familiar. This is in fact Kepler's third law for circular orbits. So that constant that we had before, that k constant, is actually 4 pi squared over the gravitational constant times the mass of the central star. Okay, so that was some results for the simple case of a circular orbit. We want to think about more general orbits. In order to do that, we're going to need to use polar coordinates for velocities. So here's a diagram. If we have the origin here, we have a point out here in the xy plane. Polar coordinates is, we look at the distance out from the origin. That's our distance r, and the angle from the positive x-axis is, we're going to call that theta. R and theta constitute polar coordinates. X and y, Cartesian coordinates. So to go from polar to Cartesian coordinates, you just have these simple equations that x is our cosine theta and y is our sine theta. To go backwards, to go from Cartesian back to polar, r is just Pythagorean theorem, square root of x squared plus y squared, and theta is the arctangent of y over x. So these are the transformation equations going back and forth between Cartesian and polar coordinates. Unit vectors in polar coordinates are kind of surprising. Our unit vectors are defined, our unit vectors depend on where you are in the plane. So if we have a point here, our displacement vector goes from the origin out to that point. R hat is going to be, again, we already defined it, it's going to be a unit vector pointing in the same direction as R. So you can write R hat as just R vector divided by its magnitude. Theta hat is a vector, that's a unit vector that's perpendicular to that R hat unit vector. And so you could define it as z hat cross r hat, where z hat is a unit vector pointing out of the page. But you don't really need to worry about that. It's just a unit vector that, again, is perpendicular to the r hat vector. So that r hat cross theta hat is pointing kind of out of the page, not into the page. Okay, so this is why unit vectors and polar coordinates are a little tricky. The point is that r hat and theta hat change direction as you move in the xy plane. So suppose this dashed line is the trajectory of a particle. Here's our particle right here. R hat points in that direction, theta hat points up. As the particle moves along this path, see the r position vector is now pointing up like this, so r hat is now pointing up. So r hat is pointing in a different direction than it originally was. So as an object moves, its unit vectors move with it. And so as the particle comes over here, now the r hat unit vector is kind of pointing up instead of over to the right. What we'll see is that we have to worry about taking the time derivative of these unit vectors because they're changing as the particle moves through space. So before we get there, what we want to do is be able to write r hat and theta hat in terms of our Cartesian unit vectors x hat and y hat. So let's let's draw our x hat and y hat unit vectors. Here's our polar unit vectors, r hat and theta hat. Let's focus on just the r hat unit vector. It's at an angle theta with respect to the x-axis. So the y component is going to be just sine theta. Remember, this has unit length, so the y component is just sine theta. The horizontal component, the x component, is just cosine theta. So what that means is that we can write r hat as cosine theta in the x hat direction and then sine of theta in the y hat direction. So we just do this from, trig by just kind of looking at our little diagram in the xy plane. We can do a similar analysis to get the components of the theta hat vector. So again, the y component is now cosine theta, and the x component is now negative sine theta. So since this angle here is the same as that angle is theta, but it's actually pointing in the negative direction, so you have to have a negative sign in front of it. So theta hat is minus sine of theta x hat plus cosine theta y hat. So we can now use these to find their time derivatives. So what we want to do is calculate the time derivative of our r hat unit vector. What we do is simply plug in our expression of r hat in terms of the Cartesian coordinates. And so now what we can do is just take the time derivative of the theta values. X hat and y hat are fixed in space, so their time derivatives are zero. They just act as constants. So when you take the time derivative of cosine theta, you get minus sine theta times x hat. The time derivative of sine theta is just cosine theta. And then, using the chain rule, you have to then take the time derivative of theta after you take the time derivative of cosine and sine. So you get a d theta dt out in front. This thing in the brackets is just what we had for theta hat. So if you flip back to the previous slide, you'll see that theta hat was minus sine theta x hat plus cosine theta y hat. So what this means is that the time derivative of the r hat vector is points in the theta hat direction, and the magnitude of it is d theta dt. So what are we supposed to make of that? How do we picture that? Well, what we're picturing, first of all, what does it mean for a unit vector to be changing in time? Well, unit vectors are always unit length, so you can't make them longer or shorter. All they can do is rotate. So if r hat is changing, it just means it's got to be rotating around the origin. So suppose it's rotating in a counterclockwise direction for increase in the increasing theta direction. So this fainter arrow is going to be the new value of r hat as it's rotating. What we found is that the time derivative of r hat is going to be in this direction. So it's going to be, so it goes from here up to there. So it changes, it goes, the change in r hat goes from here up to there. So it's in the same direction as our theta hat direction. That's what that means. And the magnitude is d theta dt. That's just the angular velocity of the object around the origin. So that's, from rigid body dynamics, you might recognize that as omega. D theta dt is omega. So you can show by a similar analysis that the time derivative of the theta hat unit vector is minus d theta dt times the r hat unit vector. So what does that mean? It means that this theta hat vector, as it goes from here down to there, that direction is pointing down and to the left. It's pointing in this direction, which is in the opposite direction of the r hat vector. So that's why it's a negative r hat. And again, the magnitude of that change is omega, d theta dt. Okay, the point of doing all this is to be able to define what a velocity vector is in polar coordinates. So let's have a particle. It's moving along this dashed line. That's its trajectory. The velocity vector is tangent to that trajectory, so it's pointing in this direction, say. This velocity vector will have two components. The radial component will be aligned in the r hat direction, and the theta, or the tangential component, will be in the theta hat direction. So we can decompose our velocity vector into vr and v theta. So let's see what this looks like. Our velocity vector is just the time derivative of the position vector. We're going to do a trick here. We're going to write that the position vector r is just its magnitude r times the r hat unit vector. Okay, so now we have the product of two variables, r with r hat, so we'll use the product rule when you're taking the derivative. Derivative of r, dr dt times r hat, plus dr hat dt times r. So again, just the product rule applied to that. And from the previous slide, we found that dr hat dt is just d theta dt times theta hat. That's the result that we just derived. And that's it. So now what we can do is we can say, well, the component of our velocity in the r hat direction, we're going to call that vr. The coefficient in front of the theta hat unit vector, we're going to call that v theta. So we can identify vr must just be dr dt. That's the radial component, dr dt. And the tangential component, v theta, must just equal r times d theta dt. We're just setting this term, v theta times theta hat, equal to this. Again, this should look familiar. The tangential or the linear velocity of something that's in rigid body rotation is just r times the angular velocity. One final derivation. We want to look at angular momentum of an object and show that it must be conserved if you have a conservative force. We want to show that this is conserved when you have a conservative force acting. So to do that, we will take the time derivative of the angular momentum vector. L is equal to r cross p. So we'll plug that in. Again, use the product rule. So we have r cross the time derivative of dp dt plus dr dt cross the momentum vector. Since momentum is mass times velocity, we can write the momentum as m, which is a constant, so we can pull it outside the derivative, times the velocity. And again, this momentum is just mass times velocity there. This term right here, mass times the time derivative of the velocity, well, that's just the same as mass times acceleration. So if the only force acting on our particle is the gravitational force, we can just write this as gravity force. The m we can bring out in front of the other one. We have mv cross v. So this first term is 0 because the gravitational force is collinear with the with that displacement vector, right? So if this is our vector pointing from, say, the sun out to our planet, the gravitational force is pointing back along that line. So whenever you have the cross product of two objects that are collinear, the angle is either 0 or 180 degrees. The cross product is 0. Same with this second one. If you take the cross product of a vector with itself, again, they're collinear, so that term also must be 0. So what this says is that the time derivative of the angular momentum vector is equal to 0. So if gravity is the only force acting on our particle, angular momentum is conserved. Okay, so again, a summary of this lecture. We have the transformation equations going from polar to Cartesian coordinates. We have unit vectors defined. We have the polar unit vectors defined in terms of the Cartesian unit vectors. We use that to define the time derivatives of our polar unit vectors. And from that, we derive this result over here, which shows us what the radial and tangential velocity vectors must be. So we'll use these results in the next lecture when we derive Kepler's laws from Newtonian mechanics.